Hey, g'day, it's Prezzo. Thanks for joining me in the workshop today. Now, I'm working on the Titan engine, and in today's episode I'm going to try to get all of the remaining operations and parts done for this engine. Now, if I get all of that completed, I'll break the engine down, I'll clean it, I'll adjust it, reassemble it with gaskets and seals, and then we can attempt to run the engine. But that will be a following episode. So I'll bring you in for a closer look at what we're doing today, but just to mention that a while ago I was very concerned that I had damaged the engine by lapping the cylinder liner with diamond lapping compound. And I was worried that some of that lapping compound might be embedded in the iron liner and might cause premature wear and tear on the piston. Now, I got in touch with Tom Lipton at Ox Tools because he was the guru that I went to when I was thinking about doing this lapping process, and I watched a lot of his videos. Now, he was kind enough to get back to me. He reassured me that any of that lapping compound that might be still present in the liner should only be very lightly adhered, and it should be possible to remove it by very, very careful cleaning. And if that was done, then I should be able to run the engine without any wear and tear on that piston. So I'm going to do that. I'll use my ultrasonic cleaner and some solvents, and in fact I'll put all of the parts through the ultrasonic cleaner before I put this back together again. But let's have a closer look at what we're going to get done today. Okay, these things are in no particular order, but these are the jobs I want to get done. So inside the Venturi there's a cylindrical brass throat, and that needs to be remachined with a taper at both ends of that throat. So I'm going to do that in the lathe with a taper turning operation and a 3-cornered scraper, and that will put that converging throat on that brass part. And the idea is that when the engine is running, it's drawing air in, and don't forget that the crankcase on these engines is essentially an air pump. So it's going to be sucking air past that spray bar, and if we can get the air to accelerate as it goes through the narrowest part of that throat, that will reduce the pressure and will act like a vacuum to suck fuel into the engine. So that's a fairly simple operation. I'm also going to make this little brass friction device here. Now, this one that you see on the engine at the moment is a prototype that I made. I'm going to do another one, but I'll make it much more accurately than this one here. And it's basically a little spring mechanism that acts on the serrations in that thimble on the needle valve. And once it's set, it should stay there. The other thing we're going to try to do is to make some bolts that attach the engine to this display stand and also the running stand. This wooden stand that you see here now, I'm not going to use that to run the engine because it'll just get damaged and oily and make a mess of it. But early on I showed the engine attached to a piece of wood, and some people said you can't use wood screws, they're not secure enough, you need to have a through bolt with a hex head, and on the back you need to have some sort of a nylock nut or a lock nut. Now I went ahead and bought some nylock nuts. Now these are 632 nylocks, zinc plated, and all of the rest of the fasteners on this engine are 632 threads. So I'm going to make some bolts that go through the wooden display stand and from the bulkhead mount. And we'll talk about the bolts in a minute because they're a bit special, but that's one more job we've got to do. And the other thing I need to do is to fix up the casting where the spray bar fits through the Venturi. Now you may recall that I machined the hole in the Venturi and then was disappointed that the boss on the casting wasn't concentric with that hole. I want to make that look right. Will have no effect whatsoever on the running of the engine, but it just bothers me and I want to get it right. So I'm going to do that on the rotary table in Bridgeport Mill. Anyway, I think that's all. I think that's all we're going to try and get done today. If I think of anything else, I'll let you know. Oh, sorry. One more thing. We have to drill the hole in the spray bar, and that is what allows fuel to run from the fuel tubing through the spray bar and into the crankcase cavity. So pretty simple job, but takes some careful setting up. Anyway, let's look at these aircraft bolts. Okay, what you're looking at here is a selection of either airframe bolts or engine bolts from full-size aircraft. Now, my late father-in-law was an aircraft mechanic with the RAF in England, and he worked in airfields west of London during the Second World War. And when he migrated to Australia, he got a job at Archfield Aerodrome, and he specialised in servicing propellers on small aircraft. But amongst these belongings was this huge container of these aircraft bolts, and I brought them home thinking I could use them for something one day. And I have actually machined other fasteners out of these bolts. They're a high strength steel alloy, and I believe they've either been cadmium plated or zinc plated. And the thread form on these is UNF. So this one here is 3/8 by 24 threads per inch. This one here is 1/4 of an inch by 28 threads per inch. And they all have markings on the heads. And I did some Googling. With this one in particular, it says GKN, and there's a number and letter code on that as well. I couldn't find anything specific about the the number code, but I did find out that GKN stood for Guest, Keen and Nettlefolds. Now they were a company that operated out of the West Midlands in England, and they formed in 1902. It was an amalgamation of several different companies, but they were manufacturers of high quality fittings and fasteners for aircraft and other military applications. So let me show you the one that I've already made. Alright, there it is. Now this is an exact replica of this particular bolt here, but scaled down until the diameter is correct for a 632 thread. Now what I did was I measured this particular bolt here, and I modeled that in Autodesk Inventor, and then I used the derived part function to make a scale replica of this one. So I scaled it down until the diameter was correct for a 632 thread. Now this all came out of a comment that I made when I was answering comments on YouTube, and I think one night I'd had a few too many glasses of wine. I went through and I was sort of typing up witty replies for all these comments, and somebody had mentioned that I should be using proper hex-headed bolts for the Titan engine. And I said, yeah, you just watch me. I'm going to make an aircraft bolt out of an aircraft bolt, and I'll single point thread it. And now, well, the chickens have come home to roost, and I actually need to do it. But rest assured, I've had a go already. As you can see, this one worked fine. So I'll show you what I did. So let's head over to lathe. I'm going to use one of these 1/4 inch bolts to make this fastener, and I'm doing it in a collet chuck because I need to be able to move the part several times. And with a small fastener like this, you need to keep everything concentric. Each time you shift the part, you want to be sure that you're not sort of introducing some error. So I'm going to start by machining off the hex head, and we'll bring it down to the major diameter of the thread. Oops, if you get it in the right speed. Right, so that's our major diameter, which in metric is 3.51 millimeters, and the shank of the bolt will need to be longer than this, but I'm just doing the portion that I'm going to thread to keep it as stiff as possible. So we're going to thread 10 millimeters in the end of the stock here. That shoulder is 15 from the end of the stock at the moment. If we get the thread right, then we can shift the part out of the collet chuck and machine the whole length of the bolt section. So this is a standard 60-degree point threading tool, single point threading tool, but it's in the tool holder upside down. So this is going to thread in the opposite direction to the way you would normally go. So we'll set that up there, and I'm going to pivot my compound slide round to 30 degrees. When I did that first fastener, I didn't do that. I just fed the tool straight in at 90 degrees to the spindle. I think pivoting around the compound is going to give us a slightly smoother thread. So this is the setup I've got. The compound slide is set around 30 degrees or 29.5 degrees if you want to be pedantic, and it's on my left, 30 degrees on my left. And what I need to do now is set the tool so that it's still perpendicular to the spindle of the lathe. So if you've got one of these little thread gauges here, you can put that on the point of your tool, and then you can adjust the tool until everything is nice and aligned. And you got to sort of look down from above and be sure you got that right. You can also move the whole arrangement in against the collet chuck in this case, but it could be the work or a chuck or something cylindrical. You can also set these up on the end of a piece of stock like that if it's wide enough, and set your tool that way. And if you're doing this, make sure you're using the metric and American side. This one here is 55 degrees, which is for English threads or Whitworth, BSF, that sort of thing. Okay, so there's the tool tip sitting right on the end of the stock, and from where I'm standing I can see that quite clearly. I'll set my DRO to 0 in that position, and then we're going to move the tool 10 millimeters into the stock, and I'm just watching my DRO here. Now, if you watch Joe Piezinski doing this on his channel, he will set a hard stop on the bed of the lathe, and then this is your start point for the thread, and you'll feed the tool in and machine the thread away from the headstock. Now, unfortunately, with the way my lathe's configured at the moment, I don't have room on the bed for a hard stop. I just physically can't clamp it because of the way the compound's set up. So I'm going to have to return the tool tip to my starting position using the DRO, and then we'll thread from there. Now, this is an imperial thread, and my lathe has an imperial lead screw, so it's no problem. I can just sort of release the half nut, come back to the start point, and rethread from that position. Okay, now although you can't see it, when I bring the tool tip in and it just touches the work, I've got my cross slide micrometer collar set to 0, and I've set the compound micrometer collar to 0 as well. And on my DRO, I've got the distance along the bed of the lathe set to 10 millimeters. So 10 millimeters inset if you like. So as long as I can return to those known positions, I can cut the thread accurately from there. Now, I've also worked out that the depth of the thread is equivalent to 21 thou measured along that 30-degree angle. So I'm going to be using my compound to set the depth of the thread, and the cross slide resetting to 0 every time. Rightio, let's go. Alright, that should be it. Now, because I only have nylock nuts, it's really hard to sort of run the nut all the way along there and check the fit. But I'll deburr this first and then we'll try it out. Alright, now I can run that on there and then it gets tight, but that's where the nylon in the end of the nut is running up against the thread. And there you go. That's working. So that's how you go. That's how you do small threads in tough material. And if you're a chicken like me and you don't want to put a thread relief in there and try to withdraw the tool at the end of the cut, starting from this left hand end and threading towards the end of the stock takes a lot of the angst out of doing this sort of thing. And it's even better if you got a stop on the bed of your lathe. The only tedious thing about this is actually looking at the DRO each time to return the tool back to its start point. Okay, now I'm going to move this out in the collet chuck and turn down the rest of the plain section of the bolt. Next thing I want to do here is to fix up this error that you can see here where the outside edge of that boss is. Now, when I drilled the hole for the spray bar, it didn't line up perfectly with the center of the cast boss there, but it did line up exactly with the center of the Venturi. So I still don't know whether it's a casting error or just the way I set up the job, but either way I want to get that looking concentric at least. So what I've done is I've got the rotary table on the Bridgeport, angle plate bolt to that. I've aligned the spindle with the center of the rotary table, and if I bolt that casting to the angle plate like that and line it up with the center of the spindle, we can go around and mill that periphery around the edge of that cast boss there and get it looking right. Now I've already done the other side. I just wanted to be sure I knew what I was doing before I showed you. And it turned out okay. You got to sort of manually shift the spindle up and down to account for the curvature of the Venturi, but you can eyeball it pretty closely. And when it came off there, I went around that with the Dremel, with a little burr, and then I finished up with a needle file, a round needle file. Later on, I'll bead blast this whole casting, and that will, give it a uniform texture where I filed it and went around there with the Dremel. Anyway, let's get set up to the other side. What I've got here is PVC block inside the crankcase. I used this previously on another operation, but it's threaded, and I've got a stud going through the angle plate with a nut on this side here. I've got an adjustable parallel that I'm putting under the face of the exhaust port, and I can loosen that stud and drop the exhaust port face down onto that adjustable parallel to line everything up, and then just lock that up. At the moment I've got this very roughly adjusted underneath this 4mm pin in the spindle of the mill, and shortly I'm going to loosen off the angle plate and lower that pin into that 4mm hole and then lock it down again, and that will align the center of the 4mm hole with the axis of the spindle. And you'll notice I've got some paper underneath the angle plate here. That's because I've only got a single 10mm screw holding the angle plate down to the rotary table, and what the paper does is just provides enough friction to make sure that nothing's going to move. It's only a very, very light cut, so I'm not too worried. Okay, so there's the pin in that 4mm hole now, and I can lock the angle plate down in that position, and then if we rotate the rotary table now, that should stay aligned with that 4mm pin. Okay, what I'm going to do is move the table over, and a lot of this is just trial and error. So we're going to lower the cutter now, start the mill, and then slowly push the casting back toward the cutter until it starts to take a cut all the way around the periphery of that hole. And then we can adjust the spindle in Z until it just touches the top of the Venturi just here and the bottom underneath here, and then we've got to adjust it to get the rest of the bits. That's cleaned up all the way around the circumference of that boss there, and when you saw me pausing, what I was doing was either raising or lowering the spindle, trying to keep track of where it was cutting. It's not perfect, but I can blend all of that with the Dremel, and I'll do that next. Whenever I do any of this sort of detail work, I keep the part close to my body, sort of lock it against your abdomen, and then I'm using the file on my right hand, and you can roll the part around. You've got your eyes directly over the top where you can see what you're doing, and you've got a bit more control this way. For an awkward part like this, it's difficult to clamp in a vise and still get all the way around it. It's just a more convenient way of doing it. And like I say, it's all about control. There's both sides done now. Looks a lot better, and when that's bead blasted, it'll look great. Okay, next job is on this little brass insert that goes inside the Venturi of the engine, and we're going to do a taper turning operation at both ends of this. So it's just a brass tube with a cross hole, and then I'm going to curve the entrance to that taper with a hand scraper. I'm going to be using this very small high-speed steel boring bar. It's been hand ground, and we're going in at a 5-degree angle to a depth of 0.6 per millimeter. That'll leave some flat on the outside here, which we can then use to bring in that curve. Right, according to my CAD model, the taper should be just reaching to the cross hole, the top edge of the cross hole there. I'm going to do the rest with this little hand scraper. It's just to put a slight curvature on the outside of that ball. Oh, there's one end done, the other end's the same, so I won't show you that. Now we're going to move on now to that little spring clip for the needle valve. Okay, this is the stock that I'll be using to make this little spring clip. Now it's 0.25mm brass shim stock. It's not been annealed, so it's still quite springy, which is what I want. And I'm going to drill a number 23 hole through one end of this sheet stock. Now that's just under 4mm, which is the diameter of our spray bar. And I'm going to clamp this down and drill it. Now, some people get really freaked out when they see people drilling holes in thin sheet stock with a normal twist drill, especially one that is not designed for brass. But I've tried this, it's completely safe. I am going to do a video coming up on how to drill large diameter holes in very thin sheet stock with normal twist drills, but that's going to have to wait until I finish the engine. Yeah, told you, perfectly safe. Now, I know this looks unduly complicated for such a simple part, but don't forget this is a very small part. It's got lots of features, made of thin sheet stock, so in my view it was worth spending the time building this steel fixture here. Now the way this will work is we're going to cut a strip off our piece of brass and we're going to screw it down to that steel block there. I'm going to use this feature on the end here to file the curve to get the full radius on the end of the brass stock. This notch that's been milled in this surface of the steel is a 90-degree V-groove. We're going to use that to form a rib in the bottom of this brass stock. And I've got another hole here which we're going to use to make a bend. Anyway, you'll see how it works. Let me get this ready. Okay, that's more than enough. I'm going to screw that down there now and we're going to scribe off the shape of the fixture. I can see those scribe lines. I'm just cutting close to the line. Thought I could see him. So I got that brass shim overhanging both sides of that fixture now and the end. So we're just going to file all of that till it's the same profile as the fixture. Okay, so that's an accurate strip with an accurate radius, and what I'll do next is I'm going to pivot this to the side and taper it a little bit, and we're also going to cut it to length. It's way too long at the moment. So you can see here I've got about 1.5 millimeters protruding from the edge of the fixture, and I'm just going to file it off to make it tapered, and then I'll do the same thing on the other side. Okay, this is the tricky bit. So what I've got here is a tiny little cold chisel that's being ground to about a 60-degree included angle, and it's got a rounded tip on it instead of a cutting edge. And I'm going to use that to forge a, what would you call it, like a rib in the back side of this piece of brass shim here. So if I line it up over the top of that 90-degree notch in the fixture, I can form that little rib, and then we're going to make a 90-degree bend and sort of curve the top away as well. Right, now I don't want to hit it too hard because it'll cut right through. So that's got me pretty close, and I'm just going to flatten that slightly. I'll come back to that later. I might sort of dress that down with a burnisher or something. Actually, I've got one. Okay, that's got that relatively flat now. This is just one of those burnishes that you use for sharpening scrapers. Alright, now I'm going to make a 90-degree bend in that now. So I've shifted our little brass piece up to the second hole, not the end one where we had it before. Now we're going to lock that down and use the same fixture to make our 90-degree bend. So there it is there now, and we're just going to squeeze that down and make the 90-degree bend. Just got to bend this a little bit past 90 degrees. That's about right there. Okay, there it is. I think that's worth the effort to make that little fixture, and what we have now is a nice accurate looking part. So this will get put aside now until we do the final assembly on the spray bar and the needle valve, and the next operation is the last one, and that's drilling the hole in the spray bar. This is the spray bar. I've got it sitting in a square collet block. It's just loose at the moment, and I'm just using the engineer square to align the hex. So if I loosen that off, you can twist the hex, right? And I'm just going to use the square there to get it right. Not that it really matters. This is just a cosmetic thing. So I think that's good. Just going to use an edge finder here to find the back of the hex and both sides of the spray bar, and then we're going to drill the hole exactly 11 millimeters from the back side of that hex. Well, that was our spotting drill. We've got to go through now with a number 52 drill bit right into the bore. Alright, that's it. That is the last part that we need to make for the engine. Happy days! Okay, here's the part that we just finished off. So there's the hole that I drilled in the milling machine. Here's the needle valve now. And that's actually not engaged on the thread, but if I start to wind that on there, if you look really carefully in that hole we just drilled, the tip of the needle valve starts to appear, and the more we wind that in, the more it covers up that hole. And because the end of the needle valve is tapered, we get that very fine fuel control. Alright, at last, this is the end of the manufacturing process. So what you're seeing in this box are all of the parts for the engine. I've still got the display stand and the fuel tank here, and what has to happen now is we need to take all of these parts. They need to be inspected, deburred, polished, cleaned, oiled and reassembled. I need to fit seals in various places on the engine, and I contacted a friend of a friend who's a model flyer, and he has some fuel that he's agreed to give me that should be suitable for this engine. Now I also have one of these. This is called a clunk tank. It's used in model aircraft. I'll be using this to run the engine in the test phase, and hopefully it's all going to run. So what will happen if the engine runs is I'll disassemble it again, and then we'll start doing all of the metal finishing processes. So we're going to anodize some parts, we're going to do some parkerizing on steel parts, we're going to bead blast the crankcase, and nickel plate some parts as well. And I'm not going to do any of that unless I'm sure the engine runs. If it's just going to be a paperweight, I'll just tidy it up and leave it like this. So in the next episode, we are going to see the engine run. Now I'll put out a reminder on YouTube just to let you know when it's about to happen. And yeah, I'm sure you're keen. I certainly am interested to see whether all of this work is going to pay off. So yeah, join me for that. It's going to be a heap of fun, hopefully. Okay, now I'm going to sign out here. Before I go, I'm going to show you my world map, and you can check to see if your pin's in the map yet. If not, let me know, and we'll catch you on the next episode. It's going to be a blast. Alrighty, Prezzo, signing out. See you next time. Yeah, as I predicted, the UK is nearly full. Check that out, Delhi, Iran, Philippines, Shenzhen in China or near Shenzhen. What else we got? South America, cool. South Africa, Australia and New Zealand.